All right, so you want to tune iNAV Altitude Hold, but before you can tune anything, you need to understand how it works. So in this video, we're going to go through the basics and details for how iNAV Altitude Hold works from top to bottom. So the first thing you need to know for iNAV Altitude Hold to work, you need to either have a barometer or GPS module. Now, both of these sensors can estimate altitude, but do not have the same amount of accuracy. Generally, a barometer is more accurate in detecting and variance in altitude changes than the GPS module. And iNAV can use sensor fusion to fuse both pieces of information together. So it can put some of the GPS module altitude data, mix that in with the barometer data, and there's variables where you can adjust an iNAV to tell it how much of each signal or sensor to use. So the three variables you're going to want to be aware of are shown here. I'm not going to repeat those because they're quite a mouthful to get on there, but it's the iNAV WZ baro P, then you got the GPS P and the GPS V. And you can see on here the descriptions. Now this is straight from the iNAV documentation. These variables are going to be available in the CLI command, so we'll show you that in a second. But the first one is the baro weighted measurement to estimate the altitude and climb rate. Same thing you can see down here, the GPS climb rate measurement to estimate the climb. And then you can see down here the weight of the GPS climb rate measurement in estimated climb rate. It's a bad write-up. But nevertheless, those are the two things. This variable right here is talking about, again, how the GPS is weighted for determining the altitude, but do note it says it is used for planes only. I have not confirmed that yet, but I'll believe that the documentation is correct. So these are two things that you're going to want to keep in mind. I don't necessarily recommend adjusting them off the bat, but if you are, obviously data, your accuracy of your altitude hold is always going to be as good as the data coming into it. So you got to keep these things in mind, and we're going to show that a little bit later in the video how you can see, do you have accurate data coming in? Is that your preliminary problem with altitude hold that you might be having and wanted to tune up a little bit better? So I found the best way to see all the altitude hold CLI variables that are there is just type in get _Z_, and that pretty much then lists them all. And there's also sonar stuff you can get as well, but you can see some of those variables here that we talked about previously or already, those three that are right here that I just showed on the screen. But there's a whole bunch more here, and you need to kind of know what these are a little bit. So just to review what's what, when you see this MC, so nav, that means a navigation mode, and it says MC, that's multicopter. But when you see FW, that's fixed wing. So obviously, if you're in a multicopter profile, when you set up iNAV, then you can ignore all these fixed wings, FW, FW, so on and so forth. Now, there's other things in here we're going to get into a little bit more, but this is the position estimator and the P term for the position estimator. Then there's the velocity. There's essentially three PID loops are running when you're in altitude hold. There's the position PID loop, the vertical velocity PID loop, and then just the PID loop to fly the quadcopter, which is your normal tuning that you're probably used to. So you got three, PID loops that you're dealing with there: position, vertical position, vertical velocity, and then just the quad's normal PID loop. So one thing that's important to note right off the bat is that you can see here in the navigation mode multicopter for position and the Z-axis, which is altitude, you can see we have a P term adjustment value, and it's currently set to 100. But down below that, and then we get into the multicopter velocity, there you got a P, an I, and a D term. Down below that, though, now you're getting into fixed wing. So this is all fixed wing. Ignore it. We're going to be talking about multicopter today. And you can see here some surface stuff. And there's a difference here. So when you look at the fixed wing variance of this, you can see that for fixed wing position Z, we have a P term, an I term, and a D term. And that's not this end. It's just not the same for multicopter. Multicopter, you just have a P term for position. So position P, and then fixed wing, you have position P, position I, position D. So it's just a little different between the two. So you see in here, when you're in multicopter mode, you have a position estimator and then a velocity estimator for the Z-axis. But when you're in fixed wing mode, you just have a position estimator. In your position estimator, you have a P, I, and a D term that you can tune. In your multicopter mode, for the position estimator, you just have a P term. Then on the velocity loop, you have a P, I, and a D term. You got that? So might be a little confusing, but at least you have me telling you about that, and you don't have to try to figure that out on your own, because in the GUI, you have to be aware of things like that to recognize this. This is a multi-copter. I have it plugged into my quad. And these values by default for integral and derivative for the position estimator, PID loop, are 0. Don't waste your time with these. They don't do anything, even if you mess with them, because there is no variables for the I term and the D term of the position estimator. Honestly, these should be grayed out in the GUI when you're in multi-copter PID loop mode and not in the PIFF, using the PIFF PID loop for flying your craft, which is a fixed wing thing. So yeah. And likewise, when you're in an airplane mode or have the PIFF controller selected for the default of what you're using for the controller, you'll see that the velocity estimator here for Z are also set to 0, 0, and 0. Well, that's because there's no variable for them. So don't mess with these numbers. Again, this should be just grayed out or just not even here when it's in fixed plane mode, but that's just not how it works, and at least in iNAV 6.1 so far. Now, this generally leads to another observation I've seen when working to tune altitude control. iNAV really could use, well, honestly, I wish multi-copter worked the same way as fixed wing, where you didn't have a Z velocity PID loop. You just had a Z position with a P, an I, and a D term. That's all you really need. That's how the fixed wing works, and it works fine. I feel like they used to both have that, but then fixed wing gets more attention, so it was changed to a position hold only or a Z position only and took out the Z velocity thing, but I could be easily wrong on that. And maybe there's a valid reason to have a Z velocity parameter or PID loop that's then controlled by the Z position. I just can't think of one off the top of my head. But if you know why, there's a really good valid reason, please do put that in the comments down below and I will pin that. Now, of course, to enable altitude hold on your quadcopter, if you have a barometer or GPS module, I'd really recommend that you have a barometer for any kind of accuracy. GPS module is just, it's not going to work super well. It depends what kind of level of accuracy you're looking for. So if you're way, way up in the sky, maybe it's fine. But anywhere kind of near the surface, you're going to really need a barometer. Nevertheless, you would tag on in the modes tab, the altitude hold mode here, and set it on a switch. So, I'm going to have it on channel 8. When I flip channel 8 up to here, up to this range, it will activate altitude hold. And the other thing you're going to want to pay attention to here under the advanced tuning tab is you're going to want to go to this hover throttle and enter generally the hover, what you're at for a hover throttle. So there you can just look in your, OSD and turn on your throttle percent. So 1,350 is 35% throttle. So if you're seeing 35% throttle generally for hover on the craft in the OSD, that's what you put in for that. From there, if you're not pleased with the altitude hold performance, what you're going to want to do is go into the PID tuning tab like we showed before. Generally, the thing that I see that you probably suspect the most is that it gets off altitude and it doesn't kind of get back up to where it should be or whatnot. So if it's taking a while to get to its original altitude after a move where it kind of seems to drop down and it stays lower, it doesn't actually get up to where it used to be altitude wise, you'd want to increase this Z position P term. Now, honestly, it really should have an I term. I'm disappointed that it doesn't have, a PI controller on this. It just has a P controller because that drift, you can just see it in the black box logs. So your best bet is increase that P term. Now you can get to a spot on that P term where you start to see bobbling, where it will go above and then below and then above and then below. And that is going to be that your P term is too high. So you can keep bumping that P term up. Once you start seeing it's kind of bobbling above and below your target altitude or where you turned on altitude hold at, then that's an indication that your P term's too high. However, it can be more complicated than that because we have this dual controller here, which I really wish we didn't have, because this altitude parameter is telling this velocity, how fast to go up or down in feet per second, meters per second, that, it could be this overshooting. So the other symptom that you generally see with altitude hold is it's not reacting fast enough. You're doing into a move, it kind of drops and you don't see those motors spinning up quick enough to kind of react. You want a faster reaction to hold that altitude. Well, again, you're going to want to bump up that Z velocity. So there again, you can go into the Z velocity P parameter and bump that up as well. If you see that it gets a little tricky here now, you almost need Blackbox to kind of thread the needle between the Z position and the V velocity Z to see which is the problem. But luckily, you're on this video and I can tell you all about that next. So to record your altitude hold, what you can do is go into your Blackbox, and what I would recommend doing is just making sure this navigation position estimator is checked on, which it is by default. You can see everything that's checked on here by default. Logging rate doesn't really matter. Just make sure Blackbox is turned on. It should record as long as you arm, so it is on by default here. Just make sure you see this, your screen set up this way. As long as you have an SD card in or you have flash space that's free space, it has space available on it, then it should record. Now you can see this flight controller doesn't register that I have a card in there because I don't, but you would either have a flash card. You might see a thing here for open flash storage. You might want to, if that's all filled, you might want to erase that, so the next time you arm, it will start to record the altitude hold position estimator and velocity estimator. Now, iNAV Blackbox files are TXT files. Don't let that throw you off. They still are Blackbox data. You're definitely going to want to download the iNAV Blackbox Explorer. Don't use the Betaflight one. The iNAV one works a little bit better. It's not as sophisticated and as polished as the Betaflight Blackbox Explorer. So I do kind of miss that, but for the navigation modes, it definitely has that kind of programmed in a little bit better, where the Betaflight just doesn't at all. It will read the black boxes, but don't use Betaflight Blackbox Explorer. Go download the iNAV Blackbox Explorer. The latest version is version 5.0. I'll have the link down below. Next, you're going to want to go to theuavtech.com/Blackbox. And there you will see I have my UAV Tech iNAV Blackbox Explorer 5.0 JSON template file that you can import in the Blackbox Explorer to follow along with our trace template setups that we're going to be talking about here in a second. Don't forget that you right click on this, you have to hit save link as. So you find this here, you right click, you hit save link as, and then save that to your computer. If you just click on it, it's not going to work right. Once you have that downloaded, place it anywhere, it doesn't matter. And then you go up to open log, and then you're going to go click that JSON file. You're going to open it just like a log file. So you can open the log file here, which I already have up, and then you click open again, and then go click the JSON file, and then that will import the workspace. So you see the workspace here. Once you have the JSON file loaded, I have the number keys on your keyboard. So not the number pad, but the keys, the numbers above the typing, the letter keys. If you hit 1, that will take you to the trace template setup for navigation mode for the roll axis. 2 is the pitch axis. 3 is the yaw axis. And then 4 is going to be the Z axis, which is altitude. And then 5 is your normal PID loop. So we have those 3 we're going to be using. And then there's more. You can go to 6. I forget, that's just pitch roll, or that's more detail on roll. For PID tuning, this is PID error. On pitch, on roll, pitch, and yaw. And then 0 is just to look at like noise, which doesn't work super well with Blackbox Explorer because they don't have these debug modes in there correctly. So if you do want to look at noise stuff for trace templates, I would get a PID toolbox, and you can use that for looking at the noise profiles and things like that for iNAV. But nevertheless, digressing here, we're going to go back to the number 4 on the keyboard, the trace template for the Z-axis or altitude or vertical position hold. In looking at this, the top one is that first PID loop. That is your target position. So you can see here, my target altitude is 1.51 meters in this scenario. And you can see that burnt yellow line, it kind of just sat. That's the altitude that the barometer was reading when I flipped into altitude hold. So that's going to stay steady. Now, the disconcerting part is that you can see my navigation position, which is this line here. That's what the quad's actually at according to the barometer. So you can see I'm at a 2.19. You can see it. I hover above it the whole time. It never gets there. So yeah, that's not ideal. And you can see the barometer is kind of popping up and down And you can, if you zoom out, the best way to really look at this altitude data is don't be so zoomed in. You can't really, see the forest through the trees. Zoom all the way out. And then you can see how my barometer reading here and how this Z, the navigation position reading, it's basically a smoothed out barometer reading. But that barometer reading is not, you'd want that to be bouncing around this burnt line. It's not. So this thing needs to be pushed down, and it's not getting there. Again, I wish I had an I term that would take out this error. So one way to do that is increase that P term. The default is 40. That's, you can see in some of the settings of the earlier video. I'm going to bump that up to 100 to hopefully get more push to bring that down to this altitude value. The next group of data right above here, this is the velocity, the vertical velocity measurements. So this position data is dictating your target velocity. So you can see this is meters per second. So it's not a position, that's not a height where this is meters. This is how fast it should be moving up or how fast it should be moving down. Again, meters per second. You have a target, and then you have an actual velocity reading. Now, again, unfortunately, in the iNAV Black Box Explorer, these are not recognized. They're not programmed in, so these are scaled, just willy-nilly, depend on how much. They're auto-scaled, which never works right. They need to be specifically put in the code to always have the same scale. So they should be lining up on top of each other. And you can notice here, see how like this, the burnt orange line is our target again. But you can see that the velocity measurement, this, this kind of teal line here, or whatever that color is, this line is way up here. But when you look at the data, you can see that, well, they're basically on top of each other. I mean, this is 0.6 or 56, and this is 0.57 meters per second. So unfortunately, in this release of Blackbox Explorer, you'll have to kind of go more by the numbers here until these get input into the code and auto scaling on them. I think I'm going to take a whack at looking at that. I think I know where I need to do that in the iNAV code, but nevertheless. Next, you have the P term, the I term, and the D term. So hopefully you're familiar with how those work and all the variables. And if you're not familiar with PID loops and how that all works, I'll drop a link down below. You got to check out my short video on the uavtech.com/tuning. There's a short video on how those terms interrelate to each other. It's key to know that. Obviously, they works just like any normal PID loop that, the P term is trying to push these terms together for sharp inputs. The I term is, over steady runs. It's trying to get that to match each other. And then the D term, and then you tune those just like a normal PID controller, which we will have in a detailed separate video coming up. We're going to go through all that with a quad in detail, but I wanted to get this one out so you at least know what the heck I'm talking about and all these little nuances with iNAV Altitude Hold. Finally, down here, you can see we have the velocity output and then the RC command throttle. Now, RC command throttle, when you have altitude turned on, Altitude Hold turned on, it is not following your throttle commands, right? You're holding the stick at that hover value. If you want to go up, you push up, just like a DJI quad, and then the quad goes up. You're not controlling the throttle at that point. The quad is, the PID loop is controlling that throttle. You want to go down, you go a little bit below your hover throttle, then the quad will go down because you're telling you're basically adjusting this navigation target position. So you can see in this part of the log, and when you're looking at these little sticks up here, again, this is not, for the roll, pitch, and yaw. Yes, this is your stick inputs when you're in just altitude hold mode. But the throttle that you see right here, that is not your throttle inputs. That is the quad, that's the PID loop throttle. So when you see this little stick go up and down, that's not me moving the sticks. If you want to see what you're moving the sticks are, that's what this RC data 3 is here. So you can see here, I'm holding, generally around 36.3% throttle. And here I move the throttle up a little bit to 40.2% throttle, and then here a little bit more. And then that will push the target. You can see here, this burnt line pushes the target up. And then after that targets get pushed up a little bit, then the quad starts to react since that P term is a little sluggish, and it will start to, you'll see the navigation position start to rise as well. So back down to the motor outputs, this is basically the motor commands from the velocity PID loop. And then this RC command is the actual, the end result, commanding the motors to, to spin up, to decrease or increase in altitude or decrease in altitude. And you can see the motor outputs conversely following that RC command. Again, your throttle is not your input anymore. It's the PID loop is doing it. You're just telling it generally what altitude you want this target to be. Do you want it to be 2.39 meters? Do you want it to be 4 meters, 5 meters? And you move your stick up to increase that up, or move your stick down to increase that down, your throttle stick, until you pull it out of altitude hold mode. And then once you're back in normal acro mode or angle mode and you have altitude hold off, of course, then you're just controlling throttle like normal. Okay, so it's a lot of information. Hopefully that was helpful in understanding some of the basics and more advanced parameters with this. You can download that UAV Tech trace templates, and you can step through those trace templates to kind of see what some of these variables are over here. I guess I have to look that way. Over here, use those trace template setups to, like, if I go to here, you can see how this target position for my roll axis is just 0, 0, 0. When it's on pitch, it's just 1, 1, 1. When it's on the yaw axis, they're not nearly as many because you don't have you're really just working with the magnetometer at that point. And then in the velocity, the Z vector, you're dealing with the 2, 2, 2, 2, 2. But again, in multicopters, you're dealing with a position estimator, then a velocity estimator, and that is used in not only, altitude hold, but also position hold as well. So you have these two PID loops that you're dealing with. And if you're having issues, I would say Blackbox Explorer is probably the easiest way to figure out which one it is. You can try trial and error by just bumping up the P term on the position estimator. But it's, it might not be so straightforward because it could be the velocity, the velocity PIDs that are a problem, not just the position PIDs. But we will get into more detailed kind of step-by-step tuning altitude hold in the next video. Again, thanks everybody for your attention and support on this. Patreon link down below if you appreciate this kind of content. Again, links down below to download, the different components of this and also that trace template thing. And I'll see you on the next one.